Welcome back. Our today's portion of discussion is the computation of inverse Laplace transform. In this computation, the method of partial fraction has a major role. So, first of all, we can have a revision of method of partial fractions. In finding inverse Laplace transform, if fs is a rational function of the form fs equal to ps by qs, where the degree of qs is greater than degree of ps, we can represent fs as a finite sum of simpler fractions called partial fractions. If in the denominator there is a linear factor of the form as plus b, the corresponding partial fraction will be capital A by as plus b, where capital A is a constant. For each repeated linear factor of the form as plus b the whole raised to n, the partial fractions are capital A1 by as plus b plus capital A2 by as plus b square plus etc. plus capital An by as plus b the whole raised to n. For a quadratic factor a square plus bs plus c in the denominator, the corresponding partial fraction will be capital As plus capital B by a square plus bs plus c. For repeated quadratic factor a square plus bs plus c the whole raised to n, these are the corresponding partial fractions. Now find L inverse of s plus 1 divided by s square into s minus 1. See, s plus 1 divided by s square into s minus 1 can be split into partial fractions. So we can write this as s plus 1 divided by s square into s minus 1. See, in denominator we have a repeated linear factor say s square and another linear factor s minus 1. So corresponding to s square, first we have a by s. Now the second term b by s square plus c divided by s minus 1. Or we can simplify this expression after taking LCM. S plus 1 is equal to as into s minus 1 plus b into s minus 1 plus c into s square plus c into s square. In this expression, first of all, we will substitute s is equal to 1. When s is equal to 1, the left hand side becomes 1 plus 1 equal to 2. S minus 1 factor goes to 0 and second goes to 0 and c. So that implies c is equal to 2. And another substitution is equal to 0. So s equal to 0 implies 1 is equal to, so the first expression 0, second 0 minus 1, that is minus b plus 0. So that implies b is equal to minus 1. And the third coefficient a can be obtained by equating coefficients of s square on both sides. So equating coefficients of s square, we have no s square on left side, so this is equal to 0. A square, so we have one a, now s square in the middle term, and coefficient of s square in the third term is c. So a plus c is equal to 0, we know the value of c, so that implies a is equal to minus c, that is minus 2. Now we can rewrite this fraction s plus 1 divided by s square into s minus 1 as minus 2 by s minus 1 by s square plus 2 by s minus 1. Therefore, L inverse of s plus 1 divided by s square into s minus 1 is equal to L inverse of minus 2 by s minus 1 by s square plus 2 divided by s minus 1. And we know that L is linear in nature, so L inverse is also linear, so we can rewrite this expression as minus 2 into L inverse of 1 by s minus L inverse of 1 by s square plus 2 into L inverse of 1 by s minus 1 using linearity property. So this is equal to, comparing with the table of transforms, we have the result minus 2 into what is L inverse of 1 by s, that is 1, minus L inverse of 1 by s square is t plus 2 into L inverse of 1 by s minus 1, that is e raised to t. So this is equal to minus 2 minus t plus 2 e raised to t. So this is the required function of this inverse Laplace transform of s plus 1 by s square into s minus 1. Consider the second problem, inverse Laplace transform of 2s square divided by s square plus 1 into s minus 1 the whole square. So using partial fractions, we can write this quotient expression as 2s square divided by s square plus 1 into s minus 1 the whole square is equal to, corresponding to the first quadratic factor s square plus 1, we have a term as plus b in the numerator divided by s square plus 1 plus c divided by s minus 1 plus d divided by s minus 1 the whole square. Now taking LCM and simplifying this expression, we have 2s square is equal to as plus b into s minus 1 the whole square plus c into s square plus 1 into s minus 1 plus d into s square plus 1. Now putting s is equal to 1, this substitution gives the hand side is 2 and the first term goes to 0 because of this s minus 1, second also goes to 0, and putting s is equal to 1 we have 2d. So that implies d is equal to 1. And another substitution, s is equal to 0 gives an expression the hand side equal to 0. So when s is equal to 0, the first bracket becomes b and second becomes 1. So this is b. And this is equal to 0. This is 1, this is minus 1, that is minus c plus d. Now we can equate the coefficients of x cube on both sides. Equating coefficients of x cube. So now x cube on left side, so we have 0. And after expansion, we have 1 x square in this factor. Multiplying this with as, we get 1 x cube. So as cube. And similarly, this s square into s cube multiplied with the c. So we have c. And now s cube in the third factor. So we have the equation a plus c is equal to 0. Now equating coefficients of s on both sides. Left side we have now s, so the coefficient is 0. And from these three expressions we can calculate the coefficients of s as a minus 2b plus c. Now collecting all these equations, we have d is equal to 1. Putting d is equal to 1 in this expression, we have minus 1 is equal to b minus c, equation number 1. And another equation, a plus c is equal to 0. A minus 2b plus c is equal to 0. And from this equation 2 and 3, equation 2 and 3 implies a plus c is equal to 2b. And a plus c is equal to 0. So these two equations implies 2b is equal to 0 or b is equal to 0. Whenever b is equal to 0, from this equation number 1, we have c is equal to 1. From equation number 1, c is equal to 1. And substituting in this equation number 2, c is equal to 1 implies from equation number 2, c is equal to 1 implies a is equal to minus c. A equal to minus c, that is minus 1. Thus we have the simpler fraction 2s square divided by s square plus 1 into s minus 1 the whole square is minus s by s square plus 1 plus 1 by s minus 1 plus 1 by s minus 1 square. Therefore, the inverse Laplace transform, L inverse of this expression equal to inverse Laplace transform of minus s by s square plus 1 inverse of 1 by s minus 1 plus L inverse of 1 by s minus 1 the whole square. Now applying standard result, this is minus of inverse Laplace transform of s by s square plus a square type. So this is cos at, that is cos t, plus this is our simple exponential function e raised to t, and this is a shifted function, that is 1 by s minus 1 the whole square. That means this is e raised to t into t. So this is the required answer.
Exercise 3. Find the inverse Laplace transform of 4s plus 5 divided by s minus 1 square into s plus 2, 2s square minus 6s plus 5 divided by s cube minus 6s square plus 11s minus 6, and s plus 2 divided by s square minus 4s plus 13.